accepted papers. And without taking too much time, I would like to welcome the first team from Simon Fraser University, Canada, to present their work on simulating a 3D scene in order to test robot algorithms. So, are you there?
Yes, hello. Let me just share my screen.
Right, thanks.
All right, so hello everyone. My name is Bronwyn Byro and I'm a bachelor's student in computing science at Simon Fraser University. Today I'll be presenting our work on the SFU StoreNav virtual human platform. 3D simulation is a standard paradigm for development and testing of robotics. It allows us to test a variety of configurations, configurations, angles, lighting conditions, and environments that may not have been encountered in real life. We also want to be able to catch errors prior to testing in the real world. If autonomous car algorithms were only tested against videos of humans from one angle, such as from the car dashboard, then it may not work when the car approaches from a different angle. Simulation can help catch these expensive and potentially dangerous errors in a safe, controlled environment. Simulating humans in virtual environments can help us to test various algorithms that require an understanding of human motion and human-robot interactions. We can test whether an autonomous vehicle can accurately assess a pedestrian as a risk, or visualize how a mobile robot navigates a crowd. While 3D simulation is highly developed in physics-based scenarios where robots interact with objects or the environment, such as robot grasping or drones, scenarios which involve humans have less realistic 3D simulations. This is due in part to the difficulty in modeling human decision-making. The Surreal dataset uses motion capture data, the simple body model, and random static backgrounds to generate a large-scale dataset of synthetic yet realistic humans. This removes the need for manually labeled data, making training data-intensive models more accessible. Similarly, the 3D People dataset is another large dataset that captures 80 subjects performing 70 different actions while wearing a variety of outfits. It is able to represent clothing geometry, which many other 3D human datasets lack. The Human Nav dataset uses the synthetic humans from the Surreal datasets and mesh scans of office buildings to create photorealistic simulations of humans in indoor office environments. While there is some work in 3D human simulation for navigation, we have identified a gap in simulating realistic human behaviors, such as variations in walking gait and speeds, as well as behavior used in retail scenarios, like inspecting products, wandering, doubling back, or periodically stopping in aisles. We aim to provide a data-driven method for simulation that can convert videos into 3D form. We also aim to capture natural human motion in a 3D simulation. In this work, we propose an extension of the SFU StoreNav dataset, which contains 108 human participants in a shopping simulation. In this experiment, participants were asked to locate and pick up items from their shopping list and interact with a Pepper robot that is programmed to help them. The dataset consists of video of each trial from 5 different angles, as well as motion capture data that collects the head position and orientation. To build the simulation, we require video and motion capture data. In the future, we aim to infer position and orientation from video only. First, we obtain pose estimates using Vibe to get a body shape and pose estimate in simple format, which is a realistic 3D model of the human body based on skinning and blend shapes. Then, the sequence of poses are imported to Blender to form an animation of a virtual human that moves through each pose in the same position within the environment. Lastly, we apply the position and orientation from the motion capture data to each frame of the animation. As a result, the virtual human moves through the environment as in the real experiments. The leftmost video here shows the original experiment with an overlay of the simple body that was produced by Vibe. As you can see, our method allows us to replay the scenario from various angles other than the original recording angle. As a proof of concept application, we used an LSTM variational autoencoder for pose forecasting. Given the simple joint parameters for the last K frames, we predict the next K frames. To test this, we randomly selected 10% of frames from each experiment as start times for the sequence, which was roughly 6,300 test sequences total. Then we compare the generated next K frames to the ground truth next K frames and calculate the mean per joint position error. This is the distance between the ground truth and prediction of averaged over each joint. Our baseline result was 0.22 meters per frame for a 2-second forecast length and 0.24 meters per frame for a 3-second forecast length. This environment is useful for algorithms that use a skeleton representation of humans, as well as for situations requiring an understanding of human motion, such as human-robot interactions, human navigational intent prediction, human pose and trajectory forecasting, and robot navigation systems. In the future, we would like to model deformable objects such as shopping bags, experiment with long-term human motion forecasting to generate novel sequences, import Blender objects into Gazebo for use with ROS, and integrate additional controllers into the 3D humans to allow them to react naturally when faced with robot interference. Thank you for your attention. Are there any questions?
Thank you for your talk. Do we have any questions from the audience? All right, then I have a small question. So it's quite interesting to use simulation for testing robotic algorithms. I think it's a nice line of research, and especially in 3D, obtaining the data is even harder than for top-down views. But the usual problem with using simulations or similar models for testing the motion prediction algorithms is that you learn to basically simulate whatever your simulation model was. Basically, if you simulate your agents with some specific model, then you learn to predict it. The prediction will basically learn to simulate this model. Do you intend to address this somehow in your work? Have you considered this?
Yeah, so I think kind of one way to avoid that is the consideration that with simulation, you can kind of get those different angles and configurations and test more than just the data that you originally have. Although it's definitely kind of that original data collection remains a big issue where you still want to have tons and tons of data to be able to very kind of thoroughly test anything, especially if it's going to be something that could potentially be expensive or unsafe to test in the real world.
Yeah, I see. And do you think this would also generalize to different obstacles layouts? So can you change slightly the position of the tables and let's say put the robot in a different place and still be able to generate some meaningful sequences?
Yeah, so currently we can only kind of automatically generate the people and the objects needed to be done manually. So that's definitely an area that we would like to further explore so that we can also sort of create the whole scene in a more data-driven manner.
Right, very nice. Then good luck with this. Thank you for your talk once again.
Thank you.
And yeah, I guess we should move on with the next spotlight talk. This one will be given by a team from the University of Stuttgart, Germany, who has developed an hierarchical predictive planner for collaborative robotics tasks. So guys, are you there?
Hey, Andre. Hey, hello everyone.
Hi.
Yeah, let me share my screen.
Thanks.
Oh, sorry, I'm here. I just been disconnected.
Oh, okay.
Okay.
All right.
Everyone see my screen?
Yes.
Okay. Okay. Thanks for being here. I'm very happy to have a chance to present our work. And hopefully it would be interesting for everyone. So our work was hierarchical prediction and planning for human-robot collaborations. So let me talk a bit about the scope. So there's 3 levels of the collaborations. Is the coexistence, cooperation, and collaboration. So basically, coexistence is every agent do their job and there's no social interaction between the agent. And the cooperation, we have some interactive and has some cooperation to do the task. So and in collaboration, we have some higher level of collaboration behavior, like the robot and the human is collaboration to do the task. And our motivation was to tackle the problem of the human-robot coordination in a sequence of manipulation tasks. For example, in the human in the kitchen task, where the robot and human had to collaborate to set up a table for the dinner. So that is our study case for this case, and we plan to integrate the human motion prediction with the task and motion blending for robotic side, so that the robot make a better informed planning from the human prediction. And we address the problem of the maximal support and minimal interference task in the mentioned setting up the table for dinner case. So our main contribution was to propose a new perspective to reduce a long-term human motion prediction by using 2 levels of planning, 2 levels of prediction. Sorry. The first, the high level would be the symbolic planning to predict a subgoal for the low level of the LSTM recurrent neural network to predict the short-term human trajectory. And then we incorporate this human trajectory into the task and motion blending logic geometric programming framework in order to have informed planning for the robot to assist the human in the setting up the table for dinner task. So as you can see here, there's a simulation for the setting up the table where the robot and human had to pick up some object from the two cells here in order to set the table. So below is the path planned for the robot given the human motion prediction. So the robot will get some of the object that the human does not get. So in order to complete the task. So without going too much for the detail, I present the overall method. So basically our system have two parts. The first part is the dynamic LGP planner, which is the task and motion planning planner for the robot, and the human motion prediction part on the right side. So first I will go into the human motion prediction part. There are two levels of the prediction here. The higher level policy will predict symbolic primitive actions, a sequence of symbolic primitive actions for the low level to plan a full pose, orientation, and position of the human. So as you can see here at below is the symbolic encoding of the state in the environment. So this number is just like there's some cup on the cell, there's some play on the cell, or there how many object on the table. So these symbolic encoded in the environment. And we have some example sequence of action primitive here to read from the start state to the end state. The action would be go to the white cell, pick up the cup, and go to the table and place. So we gathered a data set of these action primitive trajectory to train the high-level policy using imitation learning algorithm. And then, so with each action, we'll have a subgoal for each action. So the subgoal will be fit to the low-level LSTM recurrent neural network, which is encoder-decoder structure that that predict the human trajectory, short-term human trajectory given the current position and the goal. So the reason why we propose this because the well-known problem with the LSTM recurrent neural network is that it cannot predict long-term human trajectory. So we decide to propose the hierarchical prediction like this. So in order to reduce long-term human trajectory. So after reduce the long-term human trajectory, the human trajectory, the pose and orientation trajectory will be fit to the planner, and also the human symbolic predicate, which means the symbolic state of the human will be also fit to the dynamic LGP here. So so now I will go not too much detail about the dynamic LGP. So basically, as I say, the human trajectory and the human symbolic state will be fit into this algorithm. So as you can see, the algorithm will plan also two levels. The first level will be symbolic planning, which is the sequence of action primitive, and then the low level would be the nonlinear trajectory optimization problem. So you can see the main while loop here is the way we dynamic planning condition on the current environmental condition. So we had to infer the symbolic state from the current environment by this table. So we maintain a kinematic tree of the environment, and for example, we can check whether the object is on some table if there exists some join from the table to the object. So So that is the general approach of the dynamic linear site. So so I will show you a demo here to better understand how our system work. So basically, in the task instance, a human and a robot had to together get the object without interfering with each other. So the human trajectory will be fed into dynamic LHMP. At each time, the planning instant is triggered. So given the current condition, it will know which object the human would take, and it will get the other object in order to complete the task. Okay, so that's it, the end of my presentation. Thank you for your listening. Any question?
All right, thank you for the talk. If there are no questions, really, maybe we should speed up a little bit to stay in time and go on with the next spotlight talk. This one will be given by the group from KTH University in Stockholm, Sweden, and they will talk about human motion generation and reconstruction using graph-based normalizing flow. Are you ready to present?
Yes.
All right, then please share your screen.
Okay. Can you see my screen? Hello?
Yes.
Can you see my screen? Yes. Okay.
Yes.
Okay. Hello, everyone. My name is Wenjie from KTH, the Department of Robotics, Perception and Learning. I'm going to represent our work of mountain human motion generation and reconstruction using graph-based normalizing flow. Here is a short outline of the presentation. So why human motion generation and reconstruction is a challenging problem? Well, first is variability and complexity. We are very high dimensional. We could move our bodies into many kinds of poses. There are many different possible features. As for the method of motion generation, they could be categorized into deterministic and probabilistic. For the deterministic methods, they often limited to a single prediction for a given input, then fail to capture the natural variability of human motion. But probabilistic models attempt to describe a range of possible motions. The normalizing flow we use in this work is one of the probabilistic methods. Then for videos or images, there is this problem that we occlude ourselves and others. Also, we cover ourselves in clothing and so on. Due to occlusion, extracting complete skeletons in real time is challenging. For motion capture skeleton data, there also exists noise or mark missing. So in order to improve the robustness when the human skeletons are imperfect, we adopt the graph structures in the normalizing flow. I will introduce a bit about the normalizing flow first. For probabilistic generative models, there are three important families: the GAN, the VAE, and the flow-based model. All have strengths and weaknesses. With the flow-based model, we can calculate the exact log likelihood and posterior. The drawback is it's computational heavy, but for human skeletons motion capture data, it's fun. A flow-based model can transform a simple distribution into a complex one by a sequence of invertible transformation function. So the overall transformation is also invertible. A simple distribution like a Gaussian is easy for sampling and density evaluation. I don't think I have time to go for details. Here is a link about the flow-based model. The normalizing flow model has been explored for human motion synthesis in Mogul, work also in KTH by our colleagues. The Mogul is auto-regressive and uses LSTMs to enable long-term dependencies. This framework is suitable for tasks with weak control signals. The Mogul outperforms other generative techniques for human motion synthesis. Here are some examples. One challenge the generative models are facing is imperfect information. Under less controlled environments, the motion capture systems suffer from missed marker. We found when we provide the whole path sequences, but some body markers are missing, we can observe that some joints may fall apart. This situation happens occasionally. To address this problem, we extend the Mogul to graph structure. In Mogul, the coordinates of the skeleton data are concatenated to one single feature vector. We adopt the spatial temporal graph convolutional network, which has been widely applied on human body representation. To construct a skeleton graph, the motion capture data are converted to a graph structure based on the nature structure of the human skeleton. In this work, each graph node corresponds to the marker on the right. The skeleton graph can be represented as an undirected graph G. Here, V is the set of nodes and E is the set of edges. Spatial graph convolution can be defined as this equation. There also exists temporal connections that connect the same marker nodes in consecutive frames, which extends the spatial graph convolution to spatial temporal domain. This is the framework of our method for motion generation. In our models, the skeleton information is constructed as a graph. In normalizing flow, one step of flow consists of 3 layers. The activation normalization layer performs data-dependent initialization. The invertible 1x1 convolution layer performs a soft permutation, and the affine coupling layer is for transformation. We use spatial convolutional graph networks in the affine coupling layer to extract the skeleton features. And in the conditioning information, there includes the past poses. We use spatial temporal graph networks to extract the features of past sequences. The result shows when the past poses are complete, the Mogul or the Mogul with graph structures achieve comparable results. Here are some examples. However, when the past poses are incomplete, the Mogul shows unstable, and the model with graph structures are always stable. We then evaluate the result with 4th-step analysis and the bond length analysis. The 4th-step analysis is used to evaluate the force sliding artifacts in local motion synthesis. For the bond length analysis, we compare the RMSE and the standard deviation. Also, we reconstruct the missing marks with the same framework when the past sequences is incomplete. During training, the data was augmented by mirroring and time reversion. To reconstruct the missing data, we first generate the future poses, then reverse the generated poses and control signals. Regarding the reversed sequences as control information to generate markers to fill the holes of the missing data. Here are some several reconstructed examples. The blue part is missing in the historical information, and we reconstructed it. In conclusion, our model utilizes graph networks to improve the robustness of generation and reconstruct the missing marks. Now we are going to extend the graph to multiple scales and applying the framework to real scenarios. Okay, thank you for listening.
Thanks for the nice presentation. Do we have any questions this time? All right, so I have a small question. So thinking about the first talk that we heard today, the first spotlight talk, can you use this approach? Can you extend this approach for some kind of interaction between the person and some objects in the environment? Or is this currently only intended to be used in obstacle-free space, so only for generating body poses, so to say?
I think it's possible. The application could be quite widely. Nowadays, the flow-based model has been applied to human face synthesis, human gesture synthesis, and object transformation, like transform images to 3D point clouds, and to interact with the environments or some objects, we could regard this as conditional information.
Yeah, sounds good. So thanks. If we don't have any more questions, then let us continue with the last spotlight of the workshop, which comes from the UC Berkeley in the US. And the authors will speak about, again, human motion generation using meta-learning and doing so in multiple styles. So is someone ready to present?
Yeah, can you hear me? Yeah, I'm ready to present here. Just make sure it's the right screen, right?
Yes, thanks.
Okay, so
yeah, great.
Hello, everyone. Today I'll briefly introduce our work on multi-style human motion prediction generation via meta-learning. So to start with some background, usually we describe a 3D human motion by its action and its style. And the action describes what the human is actually doing, like running, walking, eating, and some regular like daily activities, while the style always represent the way the person behave, like walking in a proud way and walking in an angry way, walking in a childish way, look quite different for a different human. And there are some few intuitions that we can get from our daily experience. That is, we can determine one human's behavior only from a few frames of information. And usually with the initial poses of the person being determined and it's also its behavior being fixed, we are able to predict or generate a long horizon behavior of that person. There are a few 3D human motion related tasks. They're similar in some ways, but different in their goals. Usually, motion prediction problems aim to output the future poses of the human given its history. The behavior of the human are usually assumed to be the same. That is, if the person is walking in a certain style in the past, we won't assume the person to change its style in the future we predict. However, motion generation problems shares a similar formulation, but the generated sequence does not have ground truth poses, and therefore it should satisfy the behavior and style we define and we wish it to be. In this scenario, it is possible that we want the person to change its style in the generated future sequence. On the other hand, style transfer problems is a bit different. Usually it is defined to transfer a given pose sequence of a certain style to another style, but the operation is done usually for a whole sequence of trajectories. So The task and contribution we are trying to make here is the unsupervised styled motion generation framework. We want to learn an adaptive motion generation framework from an unlabeled dataset of styled motions. That is, we do not need labels of styles in the dataset, but for training, but we want to generate styled motion online in the generation phase. As shown in the block diagram, given the initial poses, if not specified a demonstration of another style, we are able to do prediction as just the same as the previous prediction tasks. If given a demonstration of another styled motion, we want to generate the styled motion rather than a direct forecasting of the past behaviors. For example, if given a proud demonstration of working and historically it's just working in a natural phase, that we want to generate proud working in the future rather than just prediction. One challenge for this task is the fixed horizon input. Usually in prediction, we take fixed input and output length of sequence. So we make a 3D motion and Markov decision process formulation for sequence of motions and try to learn it in an imitation learning way. If the horizon is fixed, the loss is the same as the L2 loss in the prediction. However, if the horizon is not fixed, the so-called policy learned in this way is able to handle different lengths of input. The state is designed to be a combination of the past and current poses, with the action being the current velocity actions. The reward and the initial state distribution are implicitly given in the unlabeled demonstration dataset, and we wish to learn the reward from imitation learning. For initial state distribution, we assume that for the same action like walking and running or eating, they share a similar initial state distribution. Although for different styles, they may vary a lot, but we are assuming them to be the same here. The advantage of this setting is that it removes the constraints on the past sequence length, and also the Markov property for long horizon motion is naturally satisfied in this formulation. And the policy can be adapted by changing the parameters directly or adding a context B representing the behavior in this way, so that the gradient-based meta-learning approach and memory-based meta-learning approach can all be used. Another challenge is that we need full sequence to transfer style in some previous works, and its labels. To make it in an online fashion, we use encoder for finite frames and try to maximize the mutual information between this encoded style and the motion recovered. Therefore, in generation framework, we can do a one-shot adaptation on the policy to enable an online style generation. The model is shown in this graph. Consider a trajectory generated with behavior B encoded from a demonstration. The behavior cloning loss is defined as the divergence between the input expert and the generated recovered ones. And the mutual information regularization is for the encoded style and the reconstruction motion. This will avoid the ignore of the style code for the previous model. If, for example, if the behavior code is only regarded as an augmentation to the data, it will naturally just ignore the code and just do the prediction task. We use a variational approximation for the posterior probability and to approximate the prior behavior by using sampling method. We use a memory-based meta-learning training scheme for this model, which means we're not changing the parameter of the model directly, but change the encoding of the style from demonstration each time we meet a new behavior. The output of the training phase is an inference model to infer style from sequence and a policy which outputs future behavior based on history and behavior. During one-shot testing, we infer B from a new demonstration, we update the policy, and then we generate the future sequence. For experiment, we first validate its prediction performance by comparing to previous works. We can achieve good performance on both short and long horizon settings. Notice that we do not add a lot of techniques in the encoding and the network structures, so we are not aiming for a best state-of-the-art performance in prediction tasks. We also did an ablation study on the information loss. It do has a it do have an improvement on the prediction performance. We also did it on a stylistic data set that we can predict for both for different styles using this framework. For generation validation, we fixed an initial pose and generate different style working by using different demonstrations. That is, we use the same starting poses, which is five frames with we use here, and then we show different demonstrations of neutral, proud, angry, depressed, and some childlike, which is not seen in the training data set, and then we show it to the encoder, and then we generate the future poses. We can see the style of different motion of walking. Notice that we are choosing some initial poses that appear in different styles, because if we choose a random initial state, it may happen that we cannot get a and for a conclusion, we propose a general generation framework for style motion generation. The key idea is the MDP formulation with imitation learning for flexible horizon performance and mutual information regularization for style presentation. Some potential add-ons on the encoder is to add graphic neural networks, dynamic relations, and some spatial temporal attentions. In the future work we will do is that we want to learn transitions between actions rather than styles, and then learn the initial poses distributions based on the style. Yeah, that's basically my presentation. Yeah, thank you.
Thanks, quite interesting work. Do we have any questions from the audience? One small remark from my side. I think it's an interesting work if you're able to really detect these different styles and maybe apply those this prior knowledge to better predict the future motion. Let's say for autonomous vehicle settings, do you think a similar work could be used to detect different styles of driving? Let's say if it's aggressive driver or a restrained driver.
Yeah. Actually, we have already done some like similar works in this, because the generation framework is more like meaningful for like simulation, like simulators. In simulators, we can generate different styles of human and vehicles. Maybe we can use this to test some planning algorithms to see if they can handle different scenarios correctly. Yeah, and this can naturally be used on both human motion and vehicle motion. Yeah.
Nice. All right. Thanks again for the talk. I guess